Okay, this is the lecture video for MAC 1140 Pre-Calculus. We're in section 11.1 where we're going to be taking a look at systems of linear equations. You can use either substitution or elimination. I'm going to mainly be concentrating on elimination. We'll be solving systems that have 2 variables and also systems that have 3 variables by the methods just mentioned. Wanted to remind you of a couple of scenarios graphically that explain the type of solution that you have. So here we have 3 graphs, and this shows 2 lines in each graph. Here you have 2 lines that intersect in a distinct point. So we say that right at this point of intersection, the x and the y value represent the solution to a 2-variable system. When you have something like this, okay, so this is the one solution case. When you have something like this where you have 2 lines, and each line, if you recall, is represented by an equation. But when they have no solutions, it is said that they are parallel. They don't touch. The only place that they can possibly have solutions is where the 2 lines touch. So if they don't have a point of intersection, it's because algebraically there is no solution. Okay, this is just what it looks like graphically. Then sometimes you go to find the solution for the system and the lines coincide with each other. In other words, one of the lines is directly underneath this top line, and so at every single point that is on one line, those points also belong to the other line. So we say that they have infinite solutions. Like for instance, they would touch here, and whatever those numbers are, that would be a solution. That point is on this top line and also the line that is underneath it. And then there'd be another solution, and so on. The solutions just go on and on and on. So we say that this system has infinitely many solutions. We also have some terminology that are used with respect to these 3 specific graphs. I can tell you that anytime you see the word consistent, that means that there are 1 or more solutions. Okay, this system of equations happens to touch in one and only one spot, and that point is described by these 2 values. Okay, and when you can see where this word comes from, I'll define it for you in a different way. When you can see 2 distinct lines, that is what we refer to as independent. Independent lines. Okay, inconsistent is the phrase that we give 2 lines that belong to a system that just simply don't touch. So we describe this entire situation using just the word inconsistent. Okay, that's going to be when you have no solution. Okay, one solution is described as being consistent because it has 1 or more solutions, and independent because you can see 2 distinct lines. Okay, you needn't mention the word independent when you're talking about inconsistent. You can just use this one word to describe the case where there are no solutions. So some terminology for you. When you have one line superimposed or coinciding with a line underneath it, yes, it's called consistent because consistent is a word that can be used to describe any system that has 1 or more solutions, as mentioned here. Here there was only 1 solution, but here there's more than 1 solution. These are not independent lines because you can't see 2 distinct lines. This line is superimposed on the other one. So these are called dependent lines. So instead of seeing 2 distinct separate lines, we can say only 1 line is visible, and that's because it's superimposed on top of the other line. what dependent means. So I'm just trying to describe those mathematical terms in a slightly different way so you can understand them. Okay, so consistent and dependent are the words we use to describe a situation where there are infinite solutions. Okay, now we're going to go through all of the algebraic techniques that are going to actually allow you to find either one solution, no solution, or infinitely many solutions. So some of these problems just start, on a very mild level where instead of you finding the answer from scratch, they introduce a particular set of values and they want to know, is that a solution to the system? So here you see that you have three variables. You have an equation concerning z and x. You have another equation concerning x and y. And then as your third variable, they say, and we can close this right here. There should be another set symbol right there. They say that z is any real number. Then they come down here and they give you, and this is the way solutions are presented whenever there are infinite solutions. And it even says that right here. Which of the following is one of the infinite solutions of the system? So you're going to see which one of these works in each of these equations. So for instance, let's see if it's this one. This would be your x, this would be your y, this would be your z. When you're doing ordered pairs, you can either have an ordered pair when you're talking two variables, x and y, or it's called a triple ordered pair when it's x, y, and z. And the numbers are always referred to according to the order of the alphabet. So x, this would be y, this would be z. Okay, so this being z, let's see what happens when we plug it into these expressions that have z. So like for instance, x is equal to negative z, which is 1, plus 2. Okay, I'm just copying this equation right here. I put in negative z using this z value added to, let me see what I get for x. For x, I get a 1. But yet, look at this. This value that's in the x position, which was supposed to be achieved after using this z value, it came out to be 1, but it's supposed to be 0 according to this. So this x value that we got is not equal to the value that you're seeing right there. Therefore, this can't be the answer. Okay, moving next to this one. Start with that z value. And then you can take the z value. It can be any real number. They're just asking you, is this possible as one of the triple ordered pairs? So now this time, they're calling this the z value. Go up to that equation for x. We're going to check whether using this z value of 0 could possibly give you the correct values for x and y. So let's start with x, which is opposite of the z value. We're allowing z to be 0. And then plus 2. Okay, so we end up getting 2 here. And let's see what it says x should be. This says x should be 1 when you plug this in. So, because the value we got is not equal to the value they say it should be, this can't be the solution. Okay, moving now to this triple ordered pair for C. They're using a z value of 0 once again. Start by plugging into the expression for x, and if that works out, then we'll move on to plug it in to, we'll plug in whatever we need to plug in for y. So right now we have x is opposite of z plus 2, and we're using a value of 0 for z. So we end up with a 2, and it is supposed to be a 2, so looking good so far. Next, we have to plug in and get a value for y. So let's see what we have to plug in. Okay, this is negative 2 times your x value plus 1. And we just found out what our x value, potential x value is if this is going to work out. It turned out to be 2. So put a 2 in there. Then we get negative 4 plus 1. That turns out to be negative 3. And let's see what they say it should be. That's also correct. So the y checked out. the X checked out, and because both of those checked out, giving the particular Z value that they gave in this triple ordered pair, that means this is the solution. Okay? X turned out to be 2, just like it was supposed to be, using that Z value, and Y turned out just like it was supposed to, using that Z value. And so this answer is C. Okay, moving on to number 2. In problem number 2, they give us a system of equations in 2 variables, just X and Y. So this is not an X, Y, and Z type system. So they want to know, again, on the milder level, you are not looking for these answers yourself. You're just checking answers that they are suggesting rather than you finding them. So let's see if this is really a solution to this system. Remember, for an X and a Y value to be a solution to a system, they have to satisfy both equations. So let's just check both equations. So 2 times X is 4 minus 8Y, and they're giving a Y value of 1/4. And supposedly after plugging X and Y in, we should get a 6. So let's see if that actually works out. So 2 times 4 is 8. Minus, this is 8 divided by 4, which is 2, because 8's in the numerator and this is in the denominator, so that's really right, 8 divided by 4, which is 2. 8 minus 2 is 6, so that checks out. Now we have to try these values in the second equation. So now it's 1/4 times the X value, and we have 4. Then it's minus 2 times Y, and our Y value is 1/4. And supposedly this is going to be equal to 1/2 if this X and Y truly is a solution for the system. So 4 is the same thing as 4/1, so these cancel, leaving us with 1/1 or just 1. Then it's 2 divided by 4. 2/4 is 1/2, so that's minus 1/2. And 1 take away 1/2 is 1/2. So these 2 values, 4 for X and 1/4 for Y, yes, they represent a solution for this particular system. So yes, 4 1/4 is a solution for this particular system. Okay, moving to number 3. Again, on the same level, we are not finding them. We're being given values that are suggested, which can be written like this. They can give them to you separately, what X, Y, and Z is, or they can write it as a triple ordered pair. There are 3 variables in this system. Some of the equations have all 3, and some of them do not. So let's go ahead and check. Now, we're going to have to make sure that in this particular problem, remember, what they are suggesting as a solution, those numbers have to work in every single equation. Now, if you get to an equation where it's missing one of the variables, then you just plug in the numbers for the variables that it does have. Okay, so in problem number 3, check this real quick. We have 4x is one of our terms, and we do have an x value. And we have a 3z term. And our z value is 3. Okay, that's 16 plus 9. And when we plug in, values for any of the variables that are here, it should equal 25, which it does. 16 plus 9 is 25. So that works out. Now let's get to the next equation where we only have a y and a z term, so those are the ones that we'll plug in for. So it's 4 times y, the y value is -2, and then we have minus z, and the z value here is 3. That's -8 minus 3, which is -11, and that's exactly what it's supposed to be according to these constants on the right-hand side. Okay, moving on to the last equation, which actually has all three variables, so we'll get a chance to use all three. Let's see if it satisfies. So it is opposite of x minus 5y plus 6z. Okay, let's see if that's actually equal to the 24. Using the values they've given us, x is 4. Then the y is -2, so it's -5 times y, and then it's 6 times z, and the z value they gave us in this system is 3. So this would be -4 plus 10. And if we put those two together, we get 6. And then down here we have plus 18. And when we add these two together, we get 24. Just as we were supposed to get. So, yes, this triple ordered pair for -2, 3, that is a solution for this particular system. Okay, number 4. Solve the system of equations. If the system has no solution, then say that it is inconsistent. Graph the lines of the system. So now we finally get to a problem where we are looking for the solutions ourselves. So you can use substitution or you can use elimination. Substitution's kind of nice if you like it. I mean, I prefer elimination for all of these problems, but if you are going to go the route of substitution, I'd be looking for a system where you at least have one of your variables, either the x or the y, with a coefficient of 1. Otherwise, you might want to try the elimination. So that's what I'm going to be doing. Elimination, if you recall, is when you try to get the coefficients to be the opposite sign, either for the x's or the y's. So what I'm going to go after is the x's. I'm going to try and get rid of these x's right here. That means I want these coefficients to be the same value but with different signs. So the smallest number that you can turn 15 and 4 into through multiplication is 60. I'm going to try and create 60s in front of this x as well as this one, but I have to have one of them to be negative. Because when you're doing the elimination process, after you get these to be opposite signed coefficients, you then add the equations together, which is what causes that variable to cancel. You want one column of variables to go away when you are practicing the elimination method. Okay, I'm going for 60s here. That means I'm going to be multiplying this by 4. I'll let this be my -60, so I'll just multiply it by -4. While this one I'm going to multiply by 15. And I got that 60 just by going 4 times 16. Okay, so let's see. I'm going to put out here to the side what each of these terms turn into when you multiply by 4. So you're multiplying this entire equation by -4. So it would be -60x. Then it would be -4 times -10, positive 40y. Then it will be -4 times -4 times 10 for that constant, which would be -40. Okay, going to the bottom equation, it would be 15 times everything in this bottom equation, giving you a positive 60x. 15 times 4 would be a positive 60y. And then finally 15 times 1, the constant on the other side, that would be 15. And once you have gotten either the x's where you have coefficients that are opposite signed, but the same number but with opposite signs, if you've either gotten the x or the y's to do that, well, sometimes it happens to both in certain types of solutions, then you are ready to add the equations together. Add these two equations together, and when you do so, this cancels with this. Here, when you add them together, you get 100 as the coefficient of the y term, and when you add these together, you get negative 25. Okay, continuing with that, you're now going to divide by 100 here as well as here, and you end up getting 1/4. 25 goes into itself once, 25 goes into 100 4 times, so that's 1/4, and it is negative. Bring that negative down. So this is the y value. So if we got a y value, then there's an x partner that goes with it. So the next thing that we're going to do is trying to find the x partner that goes with it. So what I'm going to use is, it's your choice what you want to use, but have part of the answer. I'm going to go and use equation 2. Numbers are a little bit smaller. So here I am continuing with equation 2. So it's 4 times x. I don't know x yet. I need to solve for it. But I do know y, which I'm going to plug in right here for 4y. It's negative 1/4. And that is equal to 1. Okay, so this is 4x. This divided by 4, 4 divided by 4 is just 1, and that would be 1 times negative 1. So you can look at it, or you can look at it like this: top times top, negative 4. Bottom times bottom, positive 4. So that's negative 4 over positive 4, negative 1. Or you can just say that cancels with that, leaving you with negative 1 over 1. In either case, you get a negative 1 there. And then we have a 1 here. Then you're going to bring this to the other side, still trying to solve for x, at which point it becomes positive 1. So now you're looking at 4x equal to 2. By the time you divide both sides by 4, you have the x partner that goes with this, which reduced is 1/2. Okay, so we say that both of the lines go through this point here. Because we do have to graph these, so that's good to know. That this is a point on both of the lines. It happens to be the point of intersection. So 1/2 your x value, and negative 1/4 is a point on both lines. Okay, so we'll make sure to remember that. It also represents the solution. The solution is a point that's on all the lines in the system. We just happen to have 2 lines. So when you're going to go graph, remember that you can try and graph in your calculator. I don't know that it's worth it in this case, but when you're going to try and graph, all you have to do is solve for y. And the minute that you solve for y in both of these equations, it's going to reveal the y-intercept. That would be one point that we could use on each of the lines. And then here is a second point, because this point actually belongs to both of the lines. You only need 2 points on each line. So for equation 1, let's get to graphing. Okay, we're trying to get this y by itself. So leave that negative 10y sitting right where it is, but bring the 15x to the other side, which would make it negative 15x. And then there also happens to be a positive 10 there. Just scoot that over. Now divide off that negative 10. That minus is really the sign that belongs to 10. So divide off that negative 10. And you have y is equal to negative 15 divided by negative 10, which would be 5 goes into the top. Let's see. 5 goes into the top 3 times, right here. 5 goes into the bottom twice, and those negatives cancel. So that's known as your slope, which we're not going to really need because we can get the graph just by using the y-intercepts and then that common point that they both go through. So to finish this, positive 10 divided by negative 10. Okay, this plain number that doesn't have an x next to it, That is known as your y-intercept. So right at 0, -1, where the y value is -1, you're going to have a point. I'm graphing the first line. A point right there on the y-intercept is a point on the y-axis. And then here's the point that they both go through. So if you just connect this, which is the y-intercept for equation 1, and you also plot that point, which happens to be a point on both of the lines, you could very easily get the graph. Okay, so I'm also going to plot 1/2 and then -1/4. I mean, it's really close, but still connecting any 2 points will get you the graph. Not for a line anyway. Okay, you might want to try a straight edge. You can do that if you'd like. Okay, so that's one of the points. And then for equation 2, I could basically do the same thing. I could use that common point that both of the lines go through, but I can also solve for y so that I can see the y-intercept. So equation 2 is this one, 4x plus 4y is equal to 1. Always leave the y term where it is. And get the 4x on the opposite side, which would make it -4x. And there was a +1 that was over on the right-hand side already. Then completely isolate that y term, because this puts it in slope-intercept form. Okay, so it would be -4 divided by 4, which would be -1. That's just your slope, but we don't need it because we're graphing just by knowing 2 points. And then we have 1/4. So this 1/4 represents the y-intercept on the other line. Oops. Right-intercept. Okay, so at 0, 1/4, you have a point that you can plot, which belongs to the second line that I'm about to graph. So at 0, 1/4, 0, 1/4, which would be about right here, 0, +1/4, be about right there. And then we also have this common point, which is already graphed. We already graphed it on the other line. Okay, once again, 0, and then go up 1/4. This is approximately up 1/4. It's not quite as high as 1/2. And then this other point, which was 1/2, and then down to -1/4. There it is right there. I'm going to connect that point and that point. I have to turn the paper around just for a second. Be able to draw a somewhat straighter line. Okay, so there's the graph that represents it. So if you're trying to put this in MyMathLab, you're going to pick a little emblem that represents what kind of picture it is. And then for a line, you're going to click on 2 points. So each time you go to graph the lines in this particular problem, you can click on this for both of the lines, and then the additional point, since you need 2 points on each line, could be this y-intercept. So remember, this was the y-intercept for equation 1, so I used that and that to get equation 1, which was this one right here. And then for equation 2, I used the y-intercept for equation 2, which was that, and once again used that common point that they both go through. If they ask you what is the point of intersection, 1/2, 1/4, right there. -1/2, -1/4. That happens to be the solution to the system. Point of intersection, right where they intersect, is the answer to the problem, which you can find algebraically, but you can also draw it. Okay, moving on to example 5. In example 5, we're going to solve the system of equations, and if the system has no solution, we're going to comment that it is inconsistent. That is the term we give to 2 lines that are parallel, that absolutely have no points in common whatsoever. Okay, so let's begin trying to solve. If you do want to try substitution, just because maybe you like that method, This might be a good opportunity for you to do so because when you have any variable that has a 1 in front of it, either the x or the y, you can solve for that particular variable. It just kind of lends itself nice to substitution if you like that method. So you would isolate the variable that has 1 as its coefficient, which would be the y right here, which means I'm going to pull the 3x to the other side. The 4 was already there, and then I'm going to substitute this into the bottom equation. So for whatever equation you have a variable with a 1 in it, you can isolate that and then substitute it into the other equation, which happens to be the bottom equation here. So you're going to actually substitute in for the variable that you isolated. So coming down to this bottom equation, we're going to go 6x plus 2y. If we're going to substitute in for y, then we need a blank spot where the y is, or else we have nowhere to substitute into. Okay, we're going to take all of this, which stands for y. There was a y in this equation, 2 times y. So we're going to substitute all of this in. Then we'll end up having 6x, and by the time we distribute that 2, we'll have negative 6x, and then 2 times 4 is 8, equal to 1. Okay, continuing with this, we have 6x and a negative 6x, so those cancel. We're left with just an 8 on this side, and presumably that's equal to 1, but of course that's a false statement. And the minute that you see a false statement, what that means is that the system is inconsistent. Which means it has no solution, and that's why you got a false statement. When you go to graph an inconsistent 2-variable system, you're going to see parallel lines. Okay, so let's get to graphing those 2 lines. In equation 1, we have 3x plus y equal to 4. You have to isolate the y if you want to graph by hand using slope-intercept. So leave the y there, bring the 3x to the other side. And we had already done this when we were going to do substitution, but I'll just do it again right here. So remember, this constant is your actual y-intercept. So right at 0, 4, you're going to plot a point. And then if you want to get another point on this line, you can just use the slope. Since we couldn't find a solution because this system didn't have a solution, we can't fall back on the method that I used in the last problem, where I used that common point right where the 2 lines hit as one of the points on each line, and the y-intercept as the other point, because you need at least 2 points to connect to get the graph of a line. But instead, since I don't have that available, I can just use this slope. In other words, referring to it as rise over run. After you make those 2 moves that represent the slope, you'll have another point. So from this 1 point that I've plotted, we're going to rise down 3, 1, 2, 3, and we're going to run 1. And then we're going to connect those. Let me turn this sideways for a minute. Okay, then let's do this for the other equation as well. So equation 2 is a 6x plus 2y. Again, trying to isolate the y term when you want to graph using the slope and y-intercept. So leave the 2y, the y term sitting where it is. Take this 6x, move it to the other side, and then there was the positive 1. Completely isolate that y term, and you'll get negative 6x divided by 2 is negative 3x. Notice how this has the same slope as this, and that's why they're parallel, because the slope is how slanted the lines are, and if they are both slanted to the same exact degree, when the slopes are equal, that's why they don't hit. That's why they're parallel. And then 1 divided by 2, that's going to be your y-intercept. So we're going to start, you always start the graph at your y-intercept. So it would be 0, 1/2, so right there. So every time I do the rise, I'm going to land at a halfway point. Just that's because that's where I'm starting. Okay, so I'm going to do slope again. My rise is -3, therefore instead of rising up 3, I'm going to be rising down 3, and then this is my run. Okay, so going down 1, down 2, down 3, and then over 1. Again, let me connect those points. Okay, and then you have 2 parallel lines. Make sure that you are familiar with this terminology. When you get a false statement as you solve your problem algebraically, that means there is no solution. The word for such a system is inconsistent. The graph turns out to be parallel lines, meaning the 2 lines don't touch, and only where they do touch is where you have a solution. So that's why this has no solution, because they do not touch. Moving to example 6. Let's see, what do we have here? Okay, so for number 6, we're going to solve the system of equations. If the system has no solution, once again, say that it is inconsistent. Okay, so I'm going to go back to the method of elimination, and I'm going to either try to get the x's to go away or the y's. I believe I'm going to go after the x's. You could use substitution if you wanted to. If you did want to use substitution, you should isolate x, get an expression for x, then substitute it into here. I'm going to use elimination. So I'm going to multiply this equation by, let's see, if that's a 7, I want this to be -7. So out here I'm going to put what results after I multiply everything by -7. So -7 times x, -7x, -7 times 5y, -35y, and then -7 times 10. So you're always using it on everything. Once you decide what you have to multiply by to make these 2 opposite signed integer coefficients. So -7 times 10, -70. Bring that bottom equation over as is, 7x, because they're already perfect. We have these matching with opposite signed integers. Okay, once you get that to happen, it's time to add the equations together. And in that addition step, the terms that have the opposite signed coefficients are going to cancel. So this cancels with this. But then we look on and we see that this is going away also. So we actually have nothing left on the left-hand side. And -70 plus 70, we have 0 left on the right side. And that does happen to be a true statement. So when all your variables disappear and you get a true statement, sorry, let me turn this phone off. This means that you have infinitely many solutions, or just infinite solutions, you could say it like that also. And so you have to get used to how to express your solutions. And this is common to every algebra book when you're solving systems. First, we'll get you used to how to express the solution for infinitely many solutions for a 2-variable system, and then we'll talk about how to do it when there's 3 variables involved. Okay, so what you're going to do for this is solve either, okay, so let's see, we're going to give it in set notation. So we're going to say that your answers are the sets of all x and y values such that y can be any real number. So, if you were given solutions, you know how x comes first and y comes last just because that's the order of these letters in the alphabet. It is always the last one. If you had an x, a y, and a z, you would talk about z can be any real number because there are infinite solutions. So that last coordinate can be any real number. And then everything else is based on expressions where any real number could be plugged into this expression. So now we need an expression for the other variable. So this can be any real number, and then you need an expression in terms of y. This is just the normal way for giving the solution for a system with infinitely many solutions. So now, as far as getting this expression that I just talked about, you can solve either one of the equations that you see up here, and that's before you multiply it by -7. Either the x plus 5y equals 10 or the 7x plus 35y equals 70. Just solve either equation for x, because we need an expression for x in terms of y. Let me try and squeeze that in here. We need an expression for x in terms of y. In terms of y. Okay, so that really just means solve for x. Okay, so I think I'm going to use this top equation right here. X plus 5y is equal to 10. So when I solve for x here, this will be -5y. Solve for x means you're getting x by itself, so this would be -5y when the 5y jumps to the other side, and then that positive 10 was already there. So that's the expression that you're going to give here at the front. X is equal to, and you'll actually feed your answer in like this. I mean, there may be a drop-down menu where they suggest it, but just in general, let me review. Whatever the last variable is in your ordered pairs, whether that be an ordered pair or a triple ordered pair, that is the one that you're going to say can be any real number, and then you're going to solve the other variables in terms of that letter. You're going to try and come up with an expression for x in terms of y. So you try to isolate the x and you'll have an expression in terms of y. Now when we get to 3 variables, I'll give you even more detail. Okay, so this says that there are infinitely many solutions and they are all of this nature. They are xy ordered pairs where y can be any real number and x can be anything where it fits this particular equation, -5y from 10, which will always come from either one of these equations you can use to give this. Okay, now let's move to example 7. So in the end, this is our final solution. Let me go ahead and do that so you're clear that that's the final solution. And here I was just making a comment as to how I got that. Okay, now we move into 3 variables. Okay, so these are a lot of work. It cannot be helped. I'm going to try and be as clear as I can as I take you through the multiple steps that it takes to get a solution from scratch. Okay, so when you're showing the work for this, just so you can follow what I'm doing, I'm going to call this equation 1. I'll call this one 2x plus y plus z and everything. I'll call this equation 2. And I'll call this equation 3. Okay, so Just like when I'm doing two variables and I'm using the elimination method, I am going to do that sort of thing here also. So my very first step that I'm going to do is I'm going to choose a variable to eliminate, and in this case I'm just going to go with the x's. I'm going to choose to try and get rid of the x's. Slightly more complicated though when you're doing a 3-variable system. So choose a variable, it's your choice. A variable to eliminate. And my choice is that I'm going to try and get rid of x. Okay, then after that, you're going to, once you decide what you're going to go for, I'm going to eliminate the chosen variable. Using 2 equations at a time. That's all you can work with is 2 equations at a time. So maybe I'll use the first, then equation 1 and 2, then I'll use equations 2 and 3. Each time my plan is that I am going to, this is my choice, I have chosen to eliminate the x term. Each time I work with 2 equations. So here's my plan. I'm going to be working first with equation 1 and 2, and I'm going to put my plan right out here. Here's how I come up with the plan. If I'm going to concentrate on equations 1 and 2, and I want the x's to go away, that means I want this to be a negative 2 because this is a positive 2. So if I want these to cancel when I add them together, as you always do when you're doing the elimination method, you have to multiply all of this in equation 1 by negative 2, so that you'll have that nice negative 2 there that will combine and cancel with this positive 2. So I'm going to take equation 1 and I'm going to multiply by negative 2, and then I'm going to add it to the equation below it, equation 2. Okay, here we go with that plan. Okay, so negative 2 times that top, every term in that top equation, so negative 2x. Negative 2 times this would be positive 6y. Then negative 2 times this would be negative 8z. And then negative 2 times this would be negative 18. Okay, then if I'm going to add it to equation 2, then I need equation 2 here. So far I did this part. I multiplied everything in equation 1 by negative 2. Negative 2x, positive 6y, negative 8z, and negative 2 times that is negative 18. Now I'm going to put equation 2 untouched, 2x plus y plus z. I'm already in a situation where the x's are going to cancel, as is my original plan to eliminate the x's, but only on 2 equations at a time. So second part of elimination, after you get those integers to be opposite signs, you add the equations, and that's what makes the variable. That's how you eliminate the variable you're trying to get rid of. So these are gone, the x's, and I end up with 6y plus 1y, 7y. So 7y, negative 8z plus 1z is negative 7z. So I have 7y minus 7z, and then I'm going to add these going down. You're just adding each column of like terms. So this plus this is negative 21. So I now have one equation, because what you are trying to do is you're trying to create 2 variable equations, because 2 variable equations are much easier to solve than 3 systems with 2 variables in it. So I'm trying to actually create a 2-variable mini system from the original 3-variable system. So far I got myself a nice equation that only has 2 variables working with equations 1 and 2. So now I'm going to shift to equations 2 and 3. Now let me look at equations 2 and 3. Now equations 2 and 3 are perfect because remember my main plan, which you need to stick to, whatever the main plan was that you chose before you started trying to get things to cancel, you want to stick with that. We're still trying to get rid of x's. So as I look at equations 2 and 3 now, I notice that these x's are already ready to cancel each other. So I actually don't have to try and create opposite signed coefficients because they're already there. Okay, so here's my plan right now, still trying to eliminate the column with x's. So I'm just going to take equation 2 and I'm going to add it to equation 3, thus creating another 2-variable equation which I can then work together, this with the one I create now. Okay, so here I go with this plan. Okay, so equation 2, I'm just going to copy it here, remove it from the main system so you can concentrate. And then negative 2x plus 3y minus 3z is equal to negative 5. I already have opposite sign integers, so I'm ready to jump into that step where I add the 2 equations together. So these cancel because they're opposite signed coefficients. And then this is 1y plus 3y. That's 4y. And then positive 1z minus 3z is negative 2z. And then this plus this is negative 8. So now I have another 2-variable equation. And what you're going to do at that point is you're going to take your smaller system that you've created that only has 2 variables in each of the equations rather than the main one. And we'll go back to the main one towards the end of the problem. So the goal now is to now use your YZ equations. Use that little mini system that we can now create that only has 2 variables. One of them was 7y minus 7z equal to negative 21, and the other one was 4y minus 2z. Now, if we can get rid of one more variable, again using elimination, we can get our first answer, and then we can back substitute to get the other 2 values. So you can now you can switch plans. Once you go from 3 variables in each of your equations, which is what we had at the beginning, to 2 variables, you can now switch plans. I was concentrating on eliminating x. Now I think what I'm going to do, it's up to you. You can either get rid of the y's or get rid of the z's. I'm just going to go for eliminating. I'll go after the y's. So if you are going to go after these, you need to change these into the same number, but one of them needs to be negative and the other one needs to be positive. So if you want an idea of what you could possibly turn both of these into, since they're both different, you can't just turn one of them into the other one because you can't turn a 7 into a 4, nor can you turn a 4 into a 7. So that means you got to change both of them. So just go 7 times 4. That's equal to 28, and that's what you can change them both into. Okay, I'm going to go for 28s. I'm going to make one of the 28s that I create as a coefficient negative while making the other one positive. Okay, so if you want to create a 28 right here, multiply by negative 4. If you want to create a 28 right here in this other y term, multiply by 7. Right out here, we can put what we get as we multiply each and every term in this top equation by negative 4. I'd have negative 28y. Then negative 4 times negative 7 would be positive 28z. And then -4 times -21 would be 84. Negative times negative is positive, so it would be positive 84. Likewise, use that multiplier out here on every term in this equation. So 7 times 4 would be positive 28y. 7 times -2 would be negative 14z. And then 7 times -8 would be negative 56. Once you have another column where they have opposite signed coefficients, you're ready to add those two equations together, thus getting rid of yet another variable. So now we're down to just a single variable here. 28 take away 14 is 14z. And then 84 take away 56 is 28 as we add this to this. Then divide off that coefficient to both sides of this little mini equation, and you finally have one value. You know that z is equal to 2. So now what we're going to do with this value is we're going to use it. We're going to scroll backwards through the equations that we've created. However, you got to be careful about where you scroll back to. Like for instance, we can go and take and plug this in, but you can't go back to the original equations yet because they have too many variables in them. So you would go and you'd plug in the z, but then you'd have two things that would be unknown. You want to plug this in somewhere where after you plug this in, there's only one unknown. Therefore, you should either be taking this, you should be taking it to any equation that you created that has this variable so that you can plug this number in, but only one other variable. That would mean you could either plug it in here or you can plug it in there. So that's exactly what I'm going to do. So I'm going to back substitute this into one of those equations. I choose this one. I'm going to go 4y minus 2z. I already know what z is. I know that it's 2, and I am about to get my second answer, the value of y. Okay, so I'm going to have 4y minus 4 is equal to -8. I'm going to bring this over here, at which point it becomes positive 4. So then I'll have 4y is equal to -4. Divide off that coefficient of positive 4, and I get y is equal to -1. So now I have a second value in this 3-variable system. Now, all the way at the end of the problem, you can finally go back to the original system that has 3 variables in it, because now you're ready for it. Because if you're going to be able to successfully use any of these equations, you need to know 2 of the 3 values. Whether you choose to use this equation, this one, or this one, that's up to you. Just pick whichever one you want and go plug in. So let's see. I'm just going to use the top equation. Okay, to finish the problem, I choose this equation, x minus 3y, going back to one of the equations, which I have chosen the top equation, in the main 3-variable system. So there's the equation that I've chosen. I already know that z is 2 and y is 1. So this is going to allow me to find x. Y is -1. Z is 2. So I'm plugging in these values that I already know so that I can get x. So this would be x plus 3 plus 8. Okay. My back's up to, let's see, let me make sure I copied this right. So it's x minus 3y plus 4z is equal to 9. Yep, I got it copied right. A lot of places to make mistakes. Okay, so minus 3 times the y value, which was -1. That gave me positive 3. And then that top equation had 4 times my z value, which did turn out to be 2. Let me see, what was my, okay. And then this is equal to 9. Okay, so I'm finishing right over here where I have some more room. I'm going to go x plus 3 plus 8, 11 is equal to 9. Finally bringing this over here and making it a -11 and finishing off with my final value, which is -2. Okay, and when you do, gain the skill in a latter class, you don't need to graph it here. You would be graphing 3 lines that look like you'd have an X, a Y, and a Z axis, and the lines look like they're coming right out of the paper, kind of like a three-dimensional effect, and right where they hit is at a triple ordered pair, and that triple ordered pair, final solution here, is x was -2, y is -1, so you can give it like this, or you can just give each of these separately, like they'll prompt you for the x, they'll prompt you for the y, and they'll prompt you for the z, and you can give each one of them separately. Okay, so that's the final solution. Quite painful. I know it is a lot of steps, but good little exercise for your brain. Okay. Wow, that's a lot. Okay, moving to example 8. Solve the system of equations. It says if the system has no solution, say that it is inconsistent. Okay. All right, so once again, you see that we are in a 3-variable system. And as I said in the last problem, you have to choose what variable you want to get rid of, and you need to get rid of that variable using 2 equations at a time. So I typically just use equation 1 and 2. So this will be equation 1, this will be equation 2, this will be equation 3. And then after I get done using equation 1 and 2 and getting rid of whatever variable I've decided to get rid of, then I get rid of that same variable. So concentrate on getting rid of the same variable twice using 2 equations at a time. So in my first attempt, I believe what I'm going to do is I think I'm going to try and get rid of the z's, only because I'm looking at equation 1 and 2, and I can see that z would be a really good variable to get rid of in this particular problem, because if you use equation 1 and 2, they're going to cancel each other out. And equation 3 doesn't even have 1. So I would really be minimizing my work if you can happen to notice something like that is going on in the problem. Try to sit there and give yourself enough time to analyze what would be the most beneficial variable to get rid of. The z's are actually going to cause me the least work. So I'm going to get rid of the z's. Okay, so to get rid, if I was using equation 1 and 2, I would simply just have to add these 2 equations. So I'm going to add equation 1 to equation 2. Okay, but actually show your work, remove those 2 equations, stack them up the way we do when we're doing elimination. We have x column, y column, z column if there is a z. Equation 2 is 3x plus 3y plus z. Okay, get those columns lined up, and then there's a 3. Let me check this. X minus y minus z is equal to 2. 3x plus 3y plus z. As you're doing these, try to check your work every so often, because there's just so many places that you can make mistakes. So I am ready to add these together, because I can already see that the z's are going to cancel. So this and this cancel, and as far as the x's, you have 1x added to 3x. So you have 4 x's. Okay, then -1 y plus 3y, you have 2y, and then that's equal to 5. So we have one mini equation in two variables, just like I did in the last problem. Okay, then when I switch to two different equations, well, at least one of them has to be different. This time I'm going to use equation, let's see, what can we do here? Well, actually, I don't have to use two more equations because I already have two different equations that actually have the same two variables and nothing more than that. That's why this was a good move. I had to actually create this equation by combining equations 1 and 2 and noticing that it would be really easy to do so since these coefficients were different. But this one's already good. So I can stack equation 3 now. So right now I'm going to take equation 3 and add it to the equation that I just created. So here's equation 3, 4x plus 2y is equal to 0. So now I have another equation right underneath it. And if I was going to try and get one more column, because once you have two equations with the same two variables, now you want to go for getting rid of a different variable. Now you want to change your perspective. At first we were trying to only have equations with z's. We were concerned with getting rid of the z's. And now I'm going to either try and get the x's to go away or the y's to go away. I think I'm going to try and turn this into a negative right here, which means I'd have to multiply all of this by -1. That would turn this into a negative, just so I don't have to write it again. It would change this into a negative, and then, because you're multiplying everything by -1. And -1 times 0, well, 0 is the only number that can't change from negative to positive. It's signless, so it's just 0. Okay, but everything else changed signs. So once you've accomplished that, add the two equations together. So positive 4x minus 4x, that's gone. Positive 2y minus 2y, that's gone. So all your variables are gone. Each time all your variables disappear, you then have to decide whether it's infinite solutions or no solution. Infinite solution is when you get the same number on both sides. And no solution is when you get a false statement. In other words, different numbers on each side where they're trying to state that those are equal, but they can't possibly be, as is the case here. When you add up these constants, you get 5. That does happen to be a false statement, and the minute that you get a false statement, the system is said to be inconsistent, meaning that there is no point that all three of these lines, because each equation represents a line, even with 3 variables, there's no point that all 3 of them run through. So this system is said to have no solution, and that's the same thing as saying inconsistent. We have certain terms that mean no solution. And we know that there's no solution because we got a false statement here. 0 is not equal to 5. Okay, moving on to example 9, where we have our third 3-variable system. Okay, shift a little bit. This is, let's see, I don't know why I have this moved all the way down here, but I guess I can use this for some space to work things out. Okay, so for example 9, okay, let's see, solve the system of equations. If the system has no solution, say that it is inconsistent. All right, so I think nothing really looks special to me. I think what I'm going to do is get rid of the x's. Okay, so again, I'm going to call this equation 1, just so you can follow the steps that I'm trying to guide you to use. So this will be equation 1, this will be equation 2, this will be equation 3, and I'm going to do some of the work up here just in this space that I have. So let's see. I think that my theme is that I am going to begin by trying to get rid of the X's. I'm going to go after those. That is your choice. I think that'll work out pretty nicely because, like, for instance, in the very first equation and second equation, if I use equation 1 and 2 and just simply add them, I don't have to force these to be opposite signed coefficients. They already are. So that's kind of a good move. So I'm going to do some work right up here. I'm going to go equation 1 plus equation 2, and I'm actually going to remove those two equations so I can concentrate on what I'm doing. It's very easy to make mistakes because there's so many steps. So you want to try and remove things from, remove the equations you're working on from the main system. So there's equation 1. I'm also concerned with equation 2, which is negative x plus 2y minus 2z is equal to negative 5. Let me check real quick that I copied everything right. X minus y minus z is 1. Negative x plus 2y minus 2z is equal to negative 5. And I can go right into that step where I add the equations. Okay, and that's because the variable that I am trying to get rid of, which is the x's, they're already ready to go. Okay, this cancels with this when I add them because they have opposite signed coefficients. When I combine this negative 1 with positive 2, I get positive 1y. And when I combine negative 1z with negative 2z, I get negative 3z. And when I combine the coefficients, 1 plus negative 5, I have negative 4. So I have one equation with less variables than what I started with, only 2 variables, so I want to create another equation like that. That's why you have to stick to the same theme. In other words, what you're trying to get rid of at least twice, so that you have 2 equations that have the same 2 variables. So I used equation 1 and 2. This time I'm going to use equation 2 and 3. All right, so let's look at equation 2 and 3. Again, trying to get rid of the x's now. So if this is 4, I want this to be negative 4. Well, the negative's already there, so what I could do is I could just multiply equation 2 by 4. It's already got that nice negative right there. That'll make it a negative 4x, and of course I'm going to multiply everything by 4. And then when I combine it with this, they'll cancel. So I'll be getting rid of x again and creating another equation that has just these 2 variables. So 4 times equation 2, adding it to equation 3. Okay, so I'm going to put here what I get. I'm going to do this first. So 4 times each and every term in equation 2. So that would give me negative 4x. Okay, then 4 times 2, that would be 8y. Then 4 times negative 2 would be negative 8z. And then 4 times negative 5 would be negative 20. Okay, negative 4, 8, negative 8z, negative 20. Okay, then I'm going to add equation 3 without any cut. My plan is not to do anything to it, just add equation 3. So let me pop that right underneath here. It's positive 4x minus 3y minus 7z, and that's equal to 0. Okay, now that I have the x column bearing opposite signed coefficients, I can now add them together because now they're ready to cancel. I'm adding each of these columns. Okay, 8 minus 3, or 8 combined with negative 3, is 5y. And then in the next column, you have the z's. So when I combine those, I have negative 8 plus negative 7. That's negative 15 on my z's. And then when I add the constants, it's negative 20 plus 0, so just negative 20. Out of room there. Okay, so let me see if I can squeeze this back in so you can read it later if you need to. So 15z This is equal to negative 20. Okay, so I have another nice equation with just y and z in it, just like I had here. So what happens at that point is that you are taking both of those equations and working them together to get your first answer. So we're going to take now use your y, z equations, the equations that just have y and z, the nice ones that you just created, create a little mini system. So you have y minus 3z is equal to negative 4. And right under it, you can stack this right under it. You have 5y minus 15z is equal to negative 20. So now that we have a smaller system, one that only has 2 variables instead of 3, we can now concentrate on getting rid of either the y's or we can get rid of the z's. I'm going to get rid of the y's. Okay, so getting rid of the y's means that if there's a positive 5 here in front of this y, I want a negative 5y here. So I'm going to take this equation and multiply it by negative 5, and I'll put the results right out here. It's better if you go sideways, because when you go down, a ton more mistakes tend to happen because you get confused and end up looking at the wrong line. But when you go across like this, you're just looking at your result. So negative 5 times y, then negative 5 times negative 3 is positive 15z. And then negative 5 times negative 4, that's 20. Bring this bottom equation over as is. So now these y's are ready to cancel. Okay, so right when they're ready to cancel, you can go ahead and add them up. So what happens is this plus this cancels. And let's see, this plus this cancels. And then this plus this cancels. So we end up getting a true statement. And anytime you get a true statement, that implies infinite solutions. So you just have to know, how do I express those infinite solutions? Now, I tried to explain this to you when we did a problem a few minutes ago, having to do with just 2 variables. I was saying that you want to express the very last variable, the one that comes last in the alphabet, as a value that could be any real number, and then you are to express the other 2 variables in terms of the variable that you said could be any real number. So let me actually put that into writing. Okay, so first thing that we're going to do, notice that in this particular system you have an x, a y, and a z. The ordered pairs, the final solutions look like this. So the very last variable, you're going to say that z can be any real number. We're going to start off assuming that z can be any real number, and then we're going to come up with expressions in terms of z. Okay, when you are doing this, you want to start by going to your equations, your mini equations that only have 2 variables in them, these y-z equations, because those will be much easier to express in terms of z. So the very first thing that you could do is you could make a choice. You have to choose which equation do you want to work with. Do you want to work with y minus 3z, before you multiply them, y minus 3z equal to negative 4, or do you want to work with negative 5y minus 15z minus 20? I believe what I'm going to work with is this one right here. Okay, so choose one of your y-z equations so that you can do this, creating an expression in terms of z. So I choose to use this one. I just looked one step up where I was working with these two variable equations. And I'm going to use y minus 3z is equal to negative 4. And if I want to get an expression for y in terms of z, that means solve for y. And when you solve for y, you'll have an equation or an equation that is written in terms of z. So just isolate the y by bringing this to the other side. So you have y is equal to, this negative 3z will come over here, now becoming a positive 3z. That negative 4 was already there. So you have an equation for y in terms of z. Remember, z can be any real number. So the last thing that you're going to need is you're going to need an expression. You now need, not an expression, an equation for x. So in other words, you're going to solve it for x, and you should have nothing but z's in it when you solve for x. You need an equation for x. So you're going to solve for x. And you should have only z's on the other side. That's called creating an equation for x in terms of z. So now what you could do is you need to go back up to the original system that has equations that have x's in them, because you can't go back to these little mini equations that you created because they only had y and z in it, and we already used those. I already used that to come up with this. Now I want to come up with an expression for x, so I can use this one, or this one, or this one. I think I'm going to use the top one. X minus y minus z is equal to 1. Okay, so this is what I'm going to do. I want to be able to solve for x. I want to isolate for x, but everything that's on the other side, I want everything else to be in terms of z. Okay, this is what you're going to solve for, but everything else should be an expression written in terms of z. So what I'm going to do is back substitute right into that y term. Okay, if I'm going to solve for this, I want these to be nothing but z's. So I do have an expression for y, so I can actually make this happen. I could go x minus y, and I can put an expression right in for y that's built out of z's, namely this one. Y is equivalent to 3z minus 4. So I'm going to put 3z minus 4 right in there for y. That's called back substituting. You're taking an expression that you created and you're plugging it in for y. Then bring down the negative z. So in this way, I'm going to be able to solve for x, and everything on the other side of the equation, once I solve for x, is going to be an expression in terms of z. Okay, let's get rid of this parentheses by applying the negative. So it's x minus 3z. So I applied it to this. I have to apply it to that. And there's a minus z. Okay, so I'm going to bring this negative 3z to the other side. It would be positive 3z. This comes over here. I'm also going to bring this over here. That'll be a positive z once it jumps over there. And I'm also going to bring this 4 over here, and it's going to be a negative 4. So we now have an expression for x, which is 4z minus 4. Okay, so we have z can be any real number, and y can be any real number plugged into this. That's how you're going to get your y value. So everything that you get for y as well as x is in terms of z, because they're created by you plugging into these equations that you created, which contain nothing but z. So in the end, when you give your final answer, you're going to give it like this. The solutions are of this form, a triple ordered pair, such that they satisfy these conditions. Okay, you can start off by mentioning the back one first. The z can be any real number. That's always mentioned at the end. And then you give your expressions for x and y, which have been created in terms of z. So x is 4z, and let me make sure that I have this right. I want to check these numbers real quick. So this was x minus 3z plus 4, and there was also a negative z, and there was a 1 over here. So that was negative, so that became positive 3z, this became positive z, so that is 4z. And then I brought a 4 over here. That's what I'm eyeballing right now. I brought this 4 over here, but I forgot to write that 1. So there was the 1 that was already there, the 4 that I brought over, and it became a negative 4, so caught it. That should have been a negative 3. Good. Okay, so x could be anything real for z, as long as it's plugged in right there. Let me just clean that up a little bit. So 4z minus 3, and then you mention what y is equal to, and y is equal to 3z minus 4. That's how you're actually going to give your solutions. And this is only in the case of infinite solutions. It's kind of, pain to give your solution, but that is how you give the solution. You give expressions for 2 of them, and the last variable is the one that you are going to state can be any real number. Oh, that one's a doozy. Okay, and the y and the z came from this and this. Okay, moving on to example 10. I don't know what happened with the spacing on this, but I guess I meant to have this on the next page. Okay, so for example 10, it says a store sells, so you have a little application problem here, which you can solve as a system, but if I can get away with not creating a system, I'm going to solve it in an easier way. Let's just see what there is in this problem. It says that we sell cashews for $6 a pound. Okay, that's $6 per pound. We also have peanuts, which are $2.50 a pound. So $2.50 per pound. And then we have one other category, which is called the mixture. So 3 categories. Cashews at $6 a pound, peanuts at $2.50 a pound, and then it says you're mixing this expensive type of nut with one that's cheaper so that you can get a price that's in between, and that would be $4 per pound. Okay, so if you wanted to come up with an equation without creating a system, I mean, they probably want you to prompt you to do a system, but you can get the answer like this. You could just say it's, now we need to know how many pounds of each we have. So let's see what we have in this problem. There's 40 pounds of peanuts. The manager decides to mix 40 pounds of peanuts with some, okay, so 40 pounds of peanuts, that's going to go right here. So 40 pounds of that. And then with some cashews, and sell the mixture at $4 per pound. So we don't know how many pounds of cashews are going to be mixed with the 40 pounds of peanuts, but we do know that the mixture will be however many pounds we have of this combined with, that's what a mixture means, that you're taking all of this and combining it with this. So this is how many pounds you will have of the $4 mixture. X plus 40 pounds of the mixture. So if you want to create an equation, you can, regarding how much you're going to be paying for each type of nut, including the mixture, it would be $6 per pound on the cashews times however many pounds of cashews you're going to use, plus it would be $2.50 per pound times the number of pounds of peanuts, which would be 40, and that it would have to be equal to $4 per pound times how many pounds the mixture is, which is X plus 40. Okay, this is how much you are spending on cashews. This is the number of pounds and $6 for each pound. So $6 times each pound. This is the number of pounds of peanuts times $2.50 for each of those 40 pounds. So you're multiplying them. Your mixture, we just know that it's this plus this combined in pounds. So it's X plus 40 pounds times $4 per pound. Okay, then to solve this, I'm going to have to finish this on the next page, 6x. So 6x plus, what I have here, got 6x plus 250 times 40. And then 4 times x plus 40. Okay, so the question here, I just copied this equation from the previous page that I had written on the previous page, and I'm going to solve for x. When we solve for x, we're going to know how many pounds of cashews should be mixed with this cheaper nut, the 40 pounds of peanuts at $2.50 per pound, in order to come up with a nice mixture that's in between these two prices. So that's what we're solving for here. So as we do this problem, I'm going to have 6x here. Then 250 times 40, you could put that in your calculator. That's 100. And then over here, it's going to be 4 times x as we distribute, and then 4 times 40. So 4x plus 160. Okay, and then to solve this, I'm going to bring all the x's over here. So I'm going to bring this over here. It'll be minus 4x, so that'll leave me with 2x. I'm also going to bring the 100 over here at this point, since we need all the constants on the opposite side. So this is gone, it's over here. This is gone, it's over here. And 160, take away 100 would be 60. And then divide by 2, and you get x is equal to 30 pounds. Okay, that completes problem number 10. Then the last problem is down here. Sorry about the spacing, but I meant for this to be further up. I'll use this space to do number 11. And I believe that's the last problem. Okay, so for number 11, we're going to find real numbers a, b, and c so that the graph of the function y is equal to ax squared plus bx plus c contains the points -1, 4, 2, 6, and 0, 2. Remember, 2 points like this means that the first one's x and the second one is y, and this is the only equation that we have to plug into. So we're going to create our own system this time, where each time we're plugging in a different x and y to create 3 different equations. Okay, I'll just put it up here. we're going to create our own system using this equation. I'll just bring this information up to the space where I'm working it so you can look at it as I'm doing it. The points that I'm going to be plugging in are negative 1, 4, 2, 6, and 0, 2. Okay, so my first equation that I'm creating is using this. Remember, I'm plugging this in for x, this in for y the first time. So for y, I would have 4 is equal to a times x squared. That x squared is negative 1. And we're going to square it plus b times x, which again is negative 1, plus the c value, which we don't have anything for. Cleaning that up a bit, this would be, now I'm going to put my variables on the left and this number on the right, because then we're going to solve it as a system. So negative 1 squared is just 1, 1a. Negative 1 times b, negative b. And then we have c, and then on the side with the constant, just a 4. You can flip-flop sides like this. Now going for equation 2. So equation 2, we have the y value. I already used that one. The y value is equal to a times the x value, which is 2 in this case. Squared says the equation. And then b times x, again the x is 2, plus c, and then I'm just going to clean it up a little bit and flip-flop the sides. So I have 4a plus 2b plus c is equal to 6. Okay, then going for equation 3. Equation 3, I'm using these two numbers. This is the x, this is the y. So my y value is 2, which goes right here in this equation. And then it's a times x squared plus b times x again plus c. So this time we end up with this gone, and just c is equal to 2. So that being the case, we can create a smaller system because it looks like it's 3 variables, but already knowing one of the variables will help us take both of these equations down to 2 variables. So going into a 2 variable smaller system. By back substituting this 2 in for this and this. Okay, so we're going to have a minus b plus 2. A minus b plus 2 is equal to 4. And then in this equation, we're going to have 4a plus 2b plus c, which again is 2, and that equation is equal to 6. Okay, then cleaning this up a little bit by bringing this 2 over here to the side where the constants are and writing it as a negative 2, we would have a minus b is equal to 2. And this equation, doing the same thing, bringing the 2 over here, writing it as a negative 2 and combining it with the 6, we would have 4a plus 2b is equal to 6 take away 2, 4. So now we have a nice little mini system, and we can just solve for a and b because we already know what c is in this particular problem. Okay, so continuing with this, I see that if I do want to get rid of the a's, you can either get rid of the a's or the b's. You'd have to multiply this top if you were going to get rid of the a's by negative 4. I'm going to go after the a's, so that would give me negative 4a, then Negative 4 times negative b would be positive 4b. And then negative 4 times 2 down here would be negative 8. And then bringing this over, it would be positive 4a, positive 2b. And bringing this one over as is, and this would be positive 4. Okay, combining these two together, negative 4 plus 4, those would cancel. 4b plus 2b is 6b. And then negative 8 plus 4 is 4. Dividing both sides by 6. And I believe this is a negative right here because negative 8 plus 4 is negative 4. That would cancel. And then this reduces. 2 goes into the top twice. And 2 goes into the bottom 3 times. So I have that. And then I need the A. Okay, so if I'm going to go after my A value, I now have the B value, the C value, and they wanted us to get A, B, and C. Okay, so let's see. I can choose either this equation. Let's just go back. You can go back to any of them, actually. You can go back to the equations that you started with at the beginning. A minus B plus C is equal to 4. You can use these equations that only have 2 variables in them. Okay, so let's see. If I went here, I'd have the B and I'd be able to get the A. So A minus B is equal to 2. So this would be A minus whatever B is, and B is negative 2/3 is equal to 2. I just chose this equation. You could have chosen that one. If you wanted to, you could have went over here and grabbed this because you actually have the C, you have the B, and you could have solved for A. You'd get the same answers. Okay, so now we have a double negative here. So this is A plus 2/3 is equal to 2, and then I'm going to bring this 2/3 over here and subtract. You can do that on your calculator if you want. So that would be 2 minus 2 divided by 3, and instead of hitting enter, hit math, enter. Math is in the first column, 4th key down. And then just hit enter, enter. And you get 4/3. So this is A is equal to 4/3. Okay, so we have all 3 values. We have our A value, we have our B value, and we have our C value. And all of this work was for problem number 11 below. I just had the space to do it up here. Okay, that concludes section 11.1, substitution and elimination to solve 2 variable systems and 3 variable